All right, so let me come back to our problem. Oh, jeebus. Sorry, everybody at home. We have hit some waves, some turbulence. Okay, so, yeah, all right. So here, 3, so here 3 is like our 10 now, isn't it, in base 3? So I got 1 here, no singles left over.
Oh.
1 and 1 is 2. And of course there's a 1. Isn't that what we got?
Huh.
Yeah.
I like it. So again, what are you really going to get out of this? Because you're not going to teach your 5-year-old kid, you're not going to teach them base 3. What you're doing right now is you are them, right? And I keep saying this, but you're experiencing this. This is the best way to make you guys remember what it felt like when you're first learning base 10. But you have beautiful manipulatives. Most everybody enjoys working with something to get the idea. Not everybody learns that way, but most people do. And then you connect it to an algorithm, right? But you can't get here until they've done enough of this to get a feel for how things kind of work. Then you can kind of make an analogy between what's going on. All right, I like it. So let's do one more. Man, you really, what a great use of paper. All right, what about this? What do you got, Jeff? What about 2, 1, 1, 1, base 3, plus 2, 1, 2, base 3? I think you hopefully have enough for that. Are you gonna have enough for that? I don't know. We'll find out.
No.
You need one more cube, don't you? Let me see. Well, we'll see what happens. If you need any extra, there's some right here. That's where things get a little more 3D. Yeah. Second. Oh, it's after the cube, and that gets weird. That requires another dimension. So I had a really good question. I mean, we are representing each place geometrically. Do they have to be represented geometrically? No. So after the place that's represented by a cube, the next thing would require 4 dimensions. You guys semi with me?
Mm-hmm.
You understand? Right? The 1 dimension, 2 dimensions, 3 dimensions. Yeah, so that's something called a hypercube. We're not going to go there. So you can imagine, it's just an interesting visual analogy that cannot go further than our reality, right? All right, that got way deeper than it had to. Sorry. Does anyone, nobody needs any extra stuff? See, this is 2 cubes, right? And then 1 flat, 1 long, and 1 poor little dude. That's 2, 1, 1, 3. I'll put you up here. 2, 1, 1, 1, base 3. And then I got 2 flats, 1 long, and 2 of these guys. Niftedelic. All right, and not surprisingly, you do it the same way we add. We start here, build our way up. So of course, these together make another one of these. This adds to these and makes one of these. These make a cube, right? Oh yeah, here's where things got freaky. Right? And then these make the next thing up, correct?
Yeah.
Because there's 3 of these now. All right, so that was a little bit tricky. So what's this mean? All right, so let's figure out what this means. So I really want this understood. I need another place now to represent this. This is one hypercube, we'll call it. So what do I have? Do I have any singles? No. Do I have any longs? No. I have a flat, right?
Mm-hmm.
And then do I have any cubes? No, because this is going to be one hypercube. One like of the next. I really want that to make sense. What do I need? How many blocks do I need till it becomes a long? 3. How many longs do I need before it becomes a flat?
3.
How many flats do I need before it becomes a cube?
3.
So I've got 3 cubes, which means I've created one. I'm just going to call it a hypercube because this is what it really would be. And I got no single cubes left, right?
Mm-hmm.
All right, let's check our work. Let's see, can we do it? Has anyone tried to do this the straight up way?
Yeah.
I didn't get too far. Yeah.
All right. 1 plus 2. I wish somebody would walk by the room or something when we say this. What is 1 plus 2? It's 10, of course, right?
Yeah.
You guys agree?
Mm-hmm.
I love it, and I would just love it. Excuse me? What do you teach my kids? All right. 1 plus 2 is 10. Everybody knows that. Carry the 1. Is everybody with me?
Yeah.
1 plus 1 plus 1 is?
3.
It's a 10.
Which is 10. Carry the 1.
2, 3, 4.
1 plus 1 plus 2 is 4.
So 1.
Which is carry the 1, and you have a
1.
1. 1 plus 2 is?
10.
10.
Cool.
Same thing, right? Base 3. Let's put base 3 down there, just to make sure. All right, let me let all that soak in for a second here. That's some tripedelic stuff, yes?
Mm-hmm.
Every base would really work the same way. Okay. All right. I'm wondering if anybody, I'm curious now, if anything exists to represent that next place up. I can imagine a couple things they could do. All right. So let's transition into pure lecture stuff. If you guys want to return those, you can. If you like them sitting, then you can do it. Okay. See where we want to fit them. Just put them on that second level down there? Yeah, thank you. I just got any container I could from that back room. There you go. Yay. Everybody? All right. So, I want to talk a little bit. I want to get to a certain point, and then I want to let you guys watch a series of 4 videos. It's going to be the same dude, some of the same little people, right? There's going to be some new little people introduced to our little math show that we watch every now and again. So 3-1 is all about addition and subtraction of whole numbers.
The screen is blue.
It's ugly.
I gotcha. So there we go. Come on, little kid. Okay. I love that it's focused. It's focused. Hey, yeah. Okay. Addition, subtraction, whole numbers. All right. We are eventually going to get into fractions. Everybody's favorite. Just not yet. So let me show you something a little bit. All right. So one way you can represent something like, let's say, 3 plus 2. you could represent it as a group of 3 distinct elements, right? It's like a weird jack-o'-lantern. So that represents the idea of 3, of course. So we'll call this A. And you got another distinct group. So it's going to be a little diamond and a rectangle. There's a mouthless version. So let me see if you guys remember this. What is NA?
3.
3. And NB?
2.
So, if I want to represent 3 plus 2, I could just take all the elements in the first dude, and it's basically a union, right? I just unioned those. You with me?
Mm-hmm.
And of course, the number that's in the union, so this would be A union B. What's the number that's in the union? 5. So that represents 3 plus 2 is 5, and we represent that with number in A plus number in B equals number in the union. All right, let me let you guys absorb that. So this is an interesting way to do it because it's the idea of number. So we have a numeral that captures the concept of number. The concept of number is what doesn't change. Every civilization we had, Mayans would be 3 blueberries, right? Babylonians would be 3 sticks, so would Egyptians, right? Romans would be basically the same thing. Right? But they had different ways to capture the same idea, and this is how we capture it. But this basic idea of just putting things together, and in the video you're going to see there's some little manipulatives, something else that we don't really have. So let me show you this. Here's how this would be. A little dude or dudette would do this. So they have a bunch of blocks, right? All right. So then the guy would say, okay, what's 3 plus 2? All right. 1, 2, 3, 4, 5. Yay. All right. So that's manipulation. That's sort of that same idea as the union kind of thing, right? Okay. That's very exciting watching a grown man counting blocks. Okay. Now, let me see, how do I say this? Let's get a little bit of specific definitions in here, just for a minute, some terminology. Terminology you might never have heard. The operation of addition is called a binary operation. What does binary mean?
2.
I really can't believe I didn't say this when we were talking about the bases, but what does binary mean? 2. It's got 2 pieces to it.
Operation of what?
Binary operation.
No, the thing you said that before. Operation of...
Oh, addition, sorry.
For some reason I thought you said division at one point.
Oh, God, no. We're nowhere near division. So that's a binary operation because it takes 2 things at a time and gives you 1 result. Okay, that's amazing, right? So almost every operation we do is binary. So if I asked you, what is 2 plus 7 plus 11, how do you do that? Do you add all 3 at once? Hell no. You do 2, and that 2 and 7 is 9. Then you add 9 and 11, so that's binary. Binary. I lock it. Something I don't really think of very often, so it's kind of funny to have this come up again. The parts of this are called either summands or addends. The parts of it. So A and B are the summands of this operation or the addends of these operations. Funkydelic. Right, so not words we use very often. So now watch, so we've got this way of doing things, of kind of introducing, and of course it's nice because you can have manipulatives for the kids to play with, makes it much more visual. Then we've got this idea. Now hopefully, I think most of you guys know this idea. How would I represent something like 2 plus 3 here on a number line?
Counting one.
You guys know? You guys remember?
It's like the
Counting on
Yeah,
days.
okay, good.
the loopy thing.
Sure, I'll do the loopy things. So each one of these, the fact that they're positive, because later we're going to use this idea to talk about subtraction. So positive number means going that way, negative numbers means going that way. Oh yeah, there's a video I kind of want to show you. So loopy loop, we're at 2. And this is sort of, if I do it this way, it sort of becomes something called counting on. So for example, if I got 2 plus 3, I start at 2 and then I count on from there 3 places, right?
Mm-hmm.
So that's kind of a nice way to do things. Start at 2 and then I count 1, 2, 3. But this by itself, let me not do the loop-de-loop. So 2, and then I go 3, and then of course I end up at 5, which still is sort of counting on also. It's just a visual counting on. So if I ask somebody, little kid, what's 5 plus 4? They can go, well, there's 5. And then 1, 2, 3, 4, 9. Okay, so they count on from one to the other. I like it. Cool. So, let me ask you something right now. What would this be? What is, and this is something based on what we just did a minute ago, but remind me again, what is 4 base 7 plus 3 base 7?
4 little cubes.
10.
Okay, you could try to go back to the manipulatives, but it's got to be 10, because it wants to be 7, but it can't be 7, right? Just like 4 and 6 is 10, 10 means 1, 0. 4 and 3 is 7, which is the base, so that's 1, 0. So how would you do this? 4 base 7 plus 5 base 7 plus 3 base 7.
Same thing.
Sort of.
Little cubes.
What would be the smart way to do that? Yeah. 4 and 3 base 7 makes, and then plus 5, 15, right? You guys with me? Sort of like if I said add 8 plus 3 plus 5 plus 2, well 8 and 2 is 10, 3 and 5 is 8, that's 18. I look for making my 10s, don't I? So if I'm in base 7, I look for making my 7. So that's one strategy for adding things. It's like my 6th puberty. One strategy for adding things is to try to create the base, right? Because everything else just kind of like falls into place. All right, now we have some incredibly exciting properties. Man, I gotta stop doing that. I really sell this big. So let's see if any of these sound familiar. Some of these hopefully sound familiar. Maybe not this first one. There's a property called closure that I can't spell for some reason. Right. Now, for some of us, closure means something psychologically, but this is
That's what
right. We need closure sometimes. But closure in mathematics means if I take 2 whole numbers, what kind of number must the result of an addition be?
Some.
Yeah, if I add 2 whole numbers, what kind of number must the result be? Another whole number. So I really want this word to make complete sense. Can I take any 2 whole numbers, add them, and get out of the set of whole numbers?
No.
Closed. Set of whole numbers is closed under addition because I can't get out of the group. There's a reason we called it closure, and I kind of like it. So our whole numbers, now think about this, our whole numbers closed under subtraction.
Yes.
What is 5 minus 7?
Oh, negative.
Is that a whole number? No, remember what's a whole number? Whole numbers start at 0, which is the number that looks like a whole, which is easy to remember for whole numbers.
And
Whole numbers don't include the idea of negative, right? Is everybody with me? So are whole numbers closed under subtraction?
No.
No, because some of the results could get out of the set of whole numbers. All right, let me stop for a minute. Has anybody ever heard of that? Or that mathematical idea of closure? But it makes sense, right?
Yeah.
Yeah.
Okay. And of course, if I multiply two whole numbers, is it closed under multiplication? What do you think?
Yes.
Definitely, right? You can't get negatives if I multiply two whole numbers. 0 times anything is still 0, right? Totally closed. Is it closed under division?
No.
Hell no. Because of course, what kind of numbers do you create when you bring division in?
All sorts of them.
You create the beautiful fractions.
Chaos.
Yeah.
Lovely chaos. Yes. Okay. So that's closure. I don't even know if I want to write anything. You guys get that? Yes.
Yeah.
Closure. Blah blah blah. All right. Oh yeah. All right. So there are two properties. Let me see if anybody remembers these words: commutative and associative.
I've heard of them, but I don't remember what they were.
Okay.
I was third grade.
Commutative. What's kind of like the root word of commutative? Commute. So commutative is when you take numbers and you move them and the result's the same. So for example, what is 2 plus 7 plus 3, is that different from 3 plus 7 plus 2? Are those different? Of course not. They're the same thing. And what happened? The 2 and the 3 just switched, so they commuted, didn't they?
Yeah.
The 2 went over there, the 3 went to this house. Yeah. Like, I'm at your house, man. I'm at your house. Shit. All right. So that's an example of the commutative property. This is where individual numbers move, commute. So that word actually makes sense. Now here's something. All right. Do you remember that thing about counting on?
Yeah.
All right. So if I asked a child, what is 9 plus 1? So they'll start at 9, and then they'll count 1 past that. Let's say 10. What could a kid do if they've gone through a lot of those examples and I say 1 plus 9?
Start with 9, add 1.
No, they would start at 1 and count 9 past. What could happen as an error there?
Adding it.
Couldn't they lose track of how much they're counting as they're going because there's too much to... All right, so it's very important that children are exposed to the idea that 1 plus 9 is the same thing as 9 plus 1, right? Which of course we just take for granted, but they don't know shit coming in because this is all stuff we made up before they were born. So, okay, I like it. So the associative's coming. Commutative property is really big because if they understand it, they can use their strategies, their learning, and make sure that they understand you don't have to start at the first number.
And it takes a shorter period of time if you do 9 plus 1.
Exactly. And real quick, there's a little hidden thing in there about teaching. When I'm teaching, I have to be careful about what examples I pick. Because if I pick examples and I don't even realize they sort of have the same thing happening, students start to believe whatever specifically happened is just what always happens, right? So teaching these properties on top of the strategies, make sure that students are able to do that on their own in case you didn't give enough examples to show that that works. I don't know if that made sense what I just said. But it's something else to keep in mind with what examples you use and how it could pigeonhole students. All right, here's my associative. Anybody remember what associative property had to do with? Let me give you 2 pictures here. Let me see how well I can draw this. All right, all right, here we go. All right. Wow. All right, that's one picture, by the way, right? So what does this caption? Let me. I didn't leave myself any room, so I'm going to have to make a much tighter little dude over here. Sorry, little dude. It's like a bowling ball, art.
Way too many balls.
What idea am I capturing here? So this is, of course, this represents angry circle. No, what is this? This is the idea of 2. Yes? Are you guys okay?
Yeah.
So I'm not going to do the little triangle and stuff. That would kill me. So this is 2. This is, of course, 4. What would be really funny, I don't, part of me just realized, I was thinking, did I make a mistake with my addition? Let's find out. 2 and 4 makes 6. And this is the idea of union, right? Combining the elements in both sets. And then I did 6 plus 1. So what's the original problem look like then? It would look like parentheses 2 plus 4 plus 1, because that means I have to add 2 and 4 first, right? So of course, what does this represent? What would it look like? What am I doing first there?
4.
4 plus 1. Do you guys all see that?
Yeah.
So I did 2 plus 4 first here, then I brought the 1 in. Here I did 4 plus 1, then I brought the 2 in. Now of course, do I end up in the same place? Of course I do. So associative is that associate, right? You associate, different groups can associate with each other. So this is kind of like reuniting in a way. So you have these disparate groups. So you can reunite these 2 together, and then you can bring him into it. And it doesn't matter what order you bring groups together. If you end up bringing them all together, it's going to end up with the same answer. Okay, that's associative property. When I teach algebra, this is what I say. Parentheses associate. What really moved from here to there? What really got up and moved? The parentheses got up and moved. That's why it's associative. So on that level, that's associative, right? For elementary school kids, you don't say that shit. You say this. You show them this picture.
No,
No?
they wouldn't understand it.
No, not the other one. Yeah, the picture hopefully. No? You don't think they'd understand the picture? This is after you've done other little things where they have a bunch of stuff on their desk, and it's 3 plus 4, so 3, 4, 7, right? They put it together, right? So they totally understand this, correct? They totally would get this, and then you're bringing that in. And there's several different ways you can do it. You can say, add the stuff. Oh yeah, I forgot. Here's one more thing, right? You could do that, right? That's the one that came in later. No? You guys okay? All right. All right. This is just trippy. It looks like a space station. Is there something else I want to say about that? No. Oh, here's one little thing. All right, this is, let me see. I gotta come up with a better example. Yeah, if I had to do something like 117 plus 35, real quick, I just want to show you something. This is sort of related to Common Core, which a lot of people enjoy beating up. There's parts of it I don't like, to be honest, but parts of it are fine. Parts that people don't understand are further thinking about how numbers work. I love it. Yeah, some of it's, some of it I don't. But watch this. Isn't this 117 plus 3 plus 32?
Yes.
Yes? So I kind of broke him up, and then I could say this is 117 plus 3 plus 32, which is 120 plus 32, which is 152. So sort of recombining the numbers in an easier way. I like it. And again, I am not up here telling you this as if I don't think you understand it, correct? I mean, this is kind of like higher level stuff, but still little kids talking about this kind of idea, just to be able to kind of do that in their head, hopefully. Okay. There's that. Those are cookie balloons. Okay. How about this property? Does this property sound familiar to anybody. How am I doing this? Okay. The identity property of addition. You guys see that? Does anyone remember what that might be, the identity property? What do you add to something and it maintains its identity? It doesn't change. 0. 0 is the additive identity because when you add something to 0, it doesn't change. You guys all with me?
Mm-hmm.
What do you think the multiplicative identity is?
1.
1. There you go. You got the idea. Identity is a thing that you operate with that doesn't change the original. So multiplicative identity 1. Additive identity 0. Kick ass. Kicking ass. So technically, it would be a plus 0 equals 0 plus a equals a. Oh, let's see. I'm trying to figure out which part I want to do. Yeah, that's true. I can do that. So let me show you. Let me just show you this right out of the book here. All right, this is where things get really interesting. I didn't want to try to copy this down myself. This is page 91 in case you have your book. Follow along.
What page is that?
91. And it's not close.
No.
Alright, so this is pretty freaking out. Some of you guys might remember multiplication tables. Kind of look like this, yes? But this is addition tables. So this is really little bit. So what they're trying to say is, based on everything that we've discussed so far, how much of this table could a kid possibly fill in? And how would it get filled in? So for example, really, the first thing I would do is, adding 0. So obviously, and also, well, let's start here. Commutativity. Why is this part kind of like shaded? What's that trying to say related to commutativity? Commutativity. What is that trying to say in relation to that? Think about this. Where is 1 plus 3 on this chart? There's 1 plus 3, maybe, right? And where's 3 plus 1? 3 plus 1 would be here. Which way did I go? 1 plus 3, so 3 plus 1 would be here.
Mm-hmm.
Okay, so everything past that diagonal, once I know this part, I automatically know this part. I like it. So see how it says 55 facts left to know, right? What the hell does that mean? How many total additions are in this table? Does everybody understand? So like 0 plus 0 is up there, correct? 0 plus 0 is up there, 1 plus 1, 1 plus 7, 6 plus 2. How many total additions are there?
5.
No? How long is this? 9?
10.
It's 10 actually, right?
10.
10 long. And that's kind of like 10 long, 100.
100.
Well, there's still 55 facts because you have to have the 0 row understood, right? Anyway, all right. So that's why it is about to be 50 because there's an extra like 0 row I've got to know something about. So the zeros are the easiest ones to fill in because that's the identity. So that you can automatically fill that stuff in. And of course, I already know this way then because that's the 0 row going this way. I like it. Then you've got the idea of counting on by 1 and 2. So that makes these easy to fill in because you can start at 1 and then count up 1 and you end up at 2. Start at 2, count up 2, you end up at 4, so forth. Okay, I like it. So it's sort of like all the strategies you provide your students, you want to make sure that they're able to use those strategies throughout all the possible numbers, right? Throughout all the possible additions. Okay. And then you've got combinations to 10, like we were talking about earlier. That's the first thing you kind of look for. So that fills in stuff like, where'd it go? 5 plus 5, 6 plus 4, so forth. Are you guys okay out there? This isn't crazy, terrible, crazy hard stuff, but it's weird. Then you got the doubles. Students normally pick up doubles pretty quickly. 1 plus 1 is 2, 2 plus 2 is 4. The idea of doubling. Let's see. Associativity comes in a few of these things. So this is going to be stuff like 9 plus 5 can be thought of as 10 plus 4. That kind of thing. So now they can figure out what 9 plus 5 is because 10 plus 4 is easy. So that's making that 10. All right. I'm really boring the shit out of you. Let me move on. Okay, we already did some of this. Yeah, so let's do this. So what process could I use, show a student to try to do something like this? How could I try to make that easier for a student to do before we've learned about carrying the one, stuff like that? What could I do? What could I let them do or show them that they could do? What do you guys think? How would you do that in your head?
Take the 1 from the 7.
Oh yeah, I love it. Okay, there you go. So it's kind of related to finding the 10, right? You're filling in this guy. So you could say this is 46 plus 1 plus 39, which is 46 plus 1 plus 39, right? So good old associativity, right? Luz is like, I wasn't thinking that shit, but this is technically what's going on, right? And then it becomes 46 plus 40. 86. Yay! What's a different way we could do this? Yes?
40 plus 30.
Yes! So 47 is 40 plus 7. 39 is 30 plus 9. So I can say 40 plus 30. So I just use associativity and commutativity together. Plus 7 plus 9. So I get 70 plus 16. 86. Yay! This is, by the way, this is the kind of stuff that I think are being reinforced less and less at the higher levels of math, because I get the students, and I have definitely over the years seen a decrease in the ability to do mental math, right? And I try to remind my colleagues that we can't fault you for what's happened to you in the education system, right? So I try to, whenever I'm teaching 88 or 90, I kind of set aside some time to just do times tables and just do, things like that, because I feel like a lot of times they're missing that. I have to do it for my calculus class too sometimes, or at least I feel like it. All right. Where's the other example? Oh yeah, okay, beautiful. Let's do this. Let me show you some of these videos. I want to make sure I get time for those. You're going to see some familiar faces. I think at least one new face. So I'll pray and see what happens with the bit of sound.
Cute kindergarten.
Kindergartners, that's right. I think this is going to be a familiar face. All right, everybody's got some problem.
All right, Carter has 9 cookies. He gave 5 cookies to his brother. How many cookies does Carter have left?
9 cookies. Take 1 5. Yes.
I love this.
Okay. Now, I noticed you did some stuff with your fingers. Can you show me up here what you did with your fingers and how you figured that out?
I did and had 5 new to equate, and then it was 4.
Okay, all right. So you had 9 cookies and you took away the 5 and you had 4 left. Got it. Okay, great.
Yeah, Wiley's got to promote himself. All right. So that's interesting, right? This is kind of neat because you're, like I said before, you're gonna have students, and it's kind of nice to kind of give students some problem without really giving them a lot of boundaries. Right? Just do what you think is gonna work, and then you want to capture what they're doing. So what he saw him doing something, you made him explain it to make sure what his thought process was. Okay. Let me see. Another kindergartner. Now this little girl, I think we've seen before. All right, real quick word, by the way. This kind of pisses me off. But they got a little girl, and they're talking about dolls, and then they get a little boy, and they talk about Transformers or something. Right? So anyway, we're all gonna work past this. It'll be fun.
Shauna has 7 dolls. For her birthday, her parents gave her 4 more dolls. How many dolls does she have altogether? So Shauna has 7 dolls. For her birthday, her parents gave her 4 more dolls. How many dolls does she have altogether? Okay.
It's gonna be neat. You gotta do this for a little while. I can love this one.
So how many dolls does she have altogether? 11. Okay, thank you very much.
Oh yeah, there's another one. That's right. By the way, real quick. Do you see what was the first thing she laid out? The 4. Why do you think she first did the 4?
And then after that, she laid down.
What was the
seven.
last number he said? 4. So he said 7 and 4. So she focused on the 4 first. Then a little prompting. She remembered the other part of the problem, right? And she's very methodical, which is kind of cool. Okay. Oh yeah, here we go. Transfer. It's amazing. Sorry.
Jake has 7 Transformers in his collection. Zach has 4 more Transformers than Jake. How many Transformers does Zach have? If you want.
11.
11. Okay, and how did you figure that out?
Count it up.
Count it up from what to what?
From 7 to 11.
Okay, and how did you use the 4? So you counted up from 7.
And use the 4 to get to 11.
Okay, so you went 7. Can you show me what you did? How you show me with your hand or something how you thought about it?
So here's 7. And it's just gonna form. If there's just 3, it would be 10.
Okay.
But it was 4, it's 11.
Okay. All right. Very good. Thank you.
So he had kind of memorized, or 7 and 3 is 10. So it was like an advanced counting up. You could do a step of 3. Okay, I like it. Which one was the? All right, we're gonna find out together. Oh, this is that.
Harrison has some cookies. He gave 3 cookies to Noah. Then he had 5 cookies left. How many cookies did Harrison start?
So he started out, I don't know how, but he started out with,
I know, that's what we need to figure out. But he gave 3 cookies to Noah. And after he gave those cookies to Noah, he had 5 cookies left. So how many cookies did he start with?
8.
How'd you figure that out?
Because I counted, because if he gave 3 to Noah and now he has 5 left, then you need to add those 3 back and then you have 8.
Okay, very good. Thank you.
I love that. All right, this one is interesting. This one, I want you, well, they'll tell you what to look for.
Ryder has 5 clay animals. During art, he made 9 more clay animals. How many clay animals does Ryder have now?
Plus, how many did I make are?
Riker had 5 clay animals. During art, he made 9 more clay animals. How many clay animals does he have? So how many?
16.
You got 16. Okay, thank you very much.
Oh,
They
okay.
they just let him leave that.
Jeez, now he's gonna forever think that. So, did you catch what happened there? I mean, what method, yeah, let's watch it again. There's a lot going on there, so I don't know if we're gonna really catch it.
For clay animals.
Alright, so he's got 5 there now, right? Yes.
He gave that one example, he said that if you start with 1, you're gonna overcount.
Yeah, alright, let's see. So, he's just got too many over there. He's got too much going on at once, right? He's got his 5 down there now. You can kind of, it's right here I was worried when he first brought all these over. Just gonna, bring all this.
Yeah.
Oh shit. And then, alright, so it kind of backs off of this. See, right there it's interesting. I'm not sure what he's doing there, to be honest. But now he kind of steps back and says, okay, 1, 2, 3. Alright, let's see, wait, where's he starting to look for 5? Here we go. Yeah, he's got the 1 in his hand. Yeah. And what's he doing with this? What's he doing?
He's counting how many he's bringing over, trying to get to 9.
Yeah, he's trying to keep track of the 9 to count on top of the 5, which is kind of related to our commutativity thing. It would have been easier if he started at 9 because he's got too much to keep track of. Plus, he didn't really keep track of his blocks well at the beginning, right?
Yeah.
So I mean, when you go to correct somebody, a child that makes this kind of mistake, you can point out what they did right and just say you have to be more careful with this, you have to write it to here, right? Okay, let me see. I just wish, that is what's missing from the end of this. I wish they would include a little discussion about what went wrong. It would be nice to see what the child does in response, right?
Yeah.
Yeah, but isn't this, I know it's upside down, that's definitely a 12 you wrote, yes?
Yeah.
So how many?
For a minute I was like,
You got 16.
it can't be just because it's upside down. Alright, so many, and then you just, alright, that's gonna piss me off. Almost as much as the dolls and the Transformers thing. Okay. Alright, so that's, yeah, I'm gonna try, we've got more than just the videos that I have access to from the publisher. I just need to get a hold of those. I was supposed to get a thumb drive with some other videos of some other students, but that never got to me. So I'm hoping we can get some more videos for us to watch, because it's really good. And I think some of them go further with just talking with the child about what they did wrong. That would be more interesting. Okay. I think I just have a couple more. Well, let's talk about this. I did show one, what do you call it? Video with the idea of subtraction in it. What have I done with my RAR? Are you in here? Yes, that's neat. Yeah, okay, so let's talk about, do I have any paper left? Sort of, not really. Talk amongst yourselves. Okay. So what about the idea of subtraction? What do you think is so there's a kind of a way to make a bridge between addition and subtraction, right? So what do you think would be kind of a way to make a problem that bridges addition and subtraction? So, I mean, I can ask a kid, what's 2 plus 5? And they'll say 7. So what if I ask them, what can I ask them instead? That I tell them 7.
7 minus 2.
So I could say, I add some number to 5, and I get 7, right? So that is, of course, the idea of subtraction built off the idea of addition. So what is one way we could use an earlier strategy to solve that kind of question? So I add some number, I just forgot what it was I had, 5, right? You get 7. I think that's what it was. So if I think about it from the standpoint of like sets of things, I have 5, and I add some number to get 7. So if I kind of showed this example, what would I do next to show how to get the answer? What would I point out next that they're sort of used to by now? Because we would have done a few examples of combining 2 sets together to make an addition. You guys sort of? So now I'm kind of like, what 2 sets? This and what other set would I combine to get that? So what can I have them do?
7 different.
Well, all right, so you're thinking ahead to
5,
subtraction. And this is,
5.
I haven't even said the word subtraction to
Count
the
up.
students yet.
Like from 5.
Yeah.
7.
So I got 5, 7, so from 5 to 7 is 6, 7. So I would need to have 2 here. So you can connect the idea of addition to illustrate the idea of subtraction even before you say the word subtraction. So you don't have to, so for example, I personally think we could introduce the idea of algebra way earlier, right? We could say, in this case, we would say 5 plus x is 7, and they're not going to freak out because we're just going, okay, x just takes the place of the thing I don't know. All right, maybe some of you guys don't agree with me, but that's right. So just be happy I'm not like Secretary of Education. But in this case, it's just 5 plus I don't know is 7. So they can do 1, 2, 3, 4, 5, 6, 7. So then they know it's 2. 2. Okay. So that's sort of a bridge between a process you used in addition and how it kind of translates into subtraction. Now, of course, when you want to get directly into full subtraction mode, you can go back to this So if I wanted to do 5 minus 2 or something here, what would I do?
Start from 5 and go down.
Yeah, if I go, so positive number means go this direction. So back 2. I could be doing the steps. 1, 2, 3, 4, 5. 1, 2 back. So now I'm at 3. All right, I like it. Okay. And you can still reinforce the idea that 5 minus 2 is 3 because 3 plus 2 is 5. It's really good to kind of hammer that home, that subtraction is directly related to addition. Okay. So how do you think, well, all right. I'm not gonna, all right, here we go, guys. All right. What do you think about this problem? Everybody understand what I'm saying here, right?
Yeah.
14 base 6 minus 5 base 6. How the hell would we do that?
Would you just wait?
All right, so let me give us a problem that we know. All right, how would I do?
Is it the same way as base 10?
How would I do 42 minus 7? Base 10. How would I do that? Borrow, yeah. If I borrow from there, what do I add to 2? I added 10. Why? Because this is the tens place. So if I had 40 and now I got 30, that must mean I put the 10 somewhere. So I love this. Do you see what this really is? This is pretending like I could put the number 12 in one spot. Do you guys see that?
Mm-hmm.
I like it. So now this is easy as shit, right? So I got 3 and I got 5. Woo-hoo. All right. Now, of course, some of you guys are like, I didn't have to borrow, but that's the point. We want to see what would we do fully. If we're just learning how to subtract in our base, we would do this. Now, don't say anything. Can you try to do that? I know you can do it. Don't say anything. It's the same exact thing we just did. You don't believe me. What is this place?
6.
Sixes. So if I borrow from it, how much am I going to add to 4? 6. What did I do here? When I borrowed from this place, what did I add to 2? 10. Why? Because that's the tens place. So if I take one of these things, aren't I taking a 10? I really want you with me. I am taking a 10. That's why that becomes 12, because I put the 10 from there onto the 2. So here, if I borrow one of these, each one of those is 6, yes?
Mm-hmm.
So I can write this as 10 now. 10 minus 5. 5, base 6. Now I know here we sort of left base 6. You with me a little bit? But I mean, that's understandable because we don't really live in base 6, but yeah, okay, maybe.
Wait, if 16 and 5 are base 10, that would be something different.
Where are we at? Sorry? Say again?
I wrote that as 16. I don't know why.
Oh, 16. Yeah, that would be good. Yeah. There. Let's check this.
I was so confused for a second. I wrote 16.
Does it make sense now that it's 14?
Yes.
Okay. So if 14 base 6 minus 5 base 6 is 5 base 6, what does 5 base 6 plus 5 base 6 better equal?
10. Oh,
14 base 6, right? All right, what is 5 base 6 plus 5 base 6?
14 base 6.
5 plus 5 wants to be 10, correct? But what would 10 be in base 6? 1 6, and how do you make 10? 4 ones. Yeah, so there you go. 5 base 6 plus 5 base 6 is 14 base 6. No?
Kind of.
A little bit. Some of you guys, yes. Some of you guys are like, aren't we close enough to just let us go? All right. I understand. Sure, why not? You can leave, actually. I think it's plenty. That's section 3.1 that we just did. Section 3.1 starts with the addition. It goes through the subtraction. If I were you, I would take a look at the homework. I would be very curious what that looks like. Take a look, bring some questions next time. And that's it. So have a good weekend.
Thank
I'm
you.
not letting you out too early. Okay. I don't feel too bad.
Good.